Hello friends, welcome to our YouTube learning channel Accurate ASME ISO. This is the most anticipated and requested video on composite positional tolerancing. Many believe that composite tolerancing is one of the toughest concepts in the GD&T. But I have spent much time creating this video to make it as simple and easy to understand. Even for complete beginners, I have included more real-world examples, graphics and animations to help you understand the concept very quickly and easily. Please do not forget to subscribe if not yet to the channel and share the video with others. Let us get started now. There are different ways to display multiple feature control frames. It is important to distinguish between a composite tolerance frame and two single segment tolerance frames because their meanings are very different. In a composite tolerance frame, there is only one position symbol common to all segments, while in two single segment tolerance frames, each segment has its own position tolerance symbol. Composite positional tolerances are used to locate the pattern of features of sizes. By providing positional tolerancing and to control the interrelationship between the features by constraining in rotation and translation within the pattern. A pattern of feature refers to at least two features arranged in a specific and defined layout. This layout can be circular, square, rectangular, or linear in the shape. There are 6 holes, that is, features of size arranged in a specific configuration known as circular hole pattern. These holes are positioned on a pitch circle diameter called as PCD of 50 with an angular pitch of 60 degrees between them. Thus, the features inside the pattern are controlled with the basic dimensions of the radiuses and angular positions between them. This is a rectangular 4-hole pattern with the holes positioned at a basic dimension of 25 horizontally and 38 in vertical. Similarly, in another arrangement shown, 3 holes are positioned in a linear pattern with a basic dimension of 20 between each hole. Composite positional tolerancing requirement is shown by the use of a composite feature control frame. The position symbol shall be entered once and shall be applicable to all horizontal segments. At a time, more than 2 horizontal segments, up to 4 levels, are allowed by the standard. This is the upper segment of composite feature control frame. It provides an application of the positional tolerancing for the location of a pattern. The pattern is considered as a single quantity as a 1 to position from the datums. In the given example, a pattern is located at 125 and 50 as basic dimensions. This is the lower segment of composite positional tolerance frame. It is used to control positional tolerancing for interrelationship of the features of the pattern. This interrelationship is controlled through basic dimensions. Here, PCD 50 and angular pitch dimension 60 degrees are the basic given dimensions. This positional tolerance controls the rotation and translation of the features within the pattern. Clause number 10.5.1b is very important. It is stated that Each lower segment is feature relating control that governs the smaller positional tolerance for each feature within the pattern. Simply, it is a feature to feature control within this smaller tolerance zone. The upper segment is pattern related tolerance zone frame, which locate the position of pattern with basic dimensions. These basic dimensions are not applicable to the location of the feature related tolerance zone frame. Feature related tolerance zone frame is nothing but lower segment. In other words, applied basic dimensions 125 and 50 do not directly control the feature of the size. Instead, the basic dimension of PCD 50 and basic angular dimension of 60 degrees govern the position of each feature. A quick difference between upper and lower segment is demonstrated here. The upper segment controls the position of the patterns, while the lower segment controls how the features within the patterns are related, limiting their rotation and translation. Understanding composite position tolerancing requires a clear understanding of the concept of constraint in the rotation and translation of an object. These constraints refer to the sixth degree of freedom, meaning the object is either allowed or restricted from moving in six possible directions, either simultaneously or individually. Let us understand the sixth degree of freedom concept using an example. 6 degrees of freedom means locating a part in datum reference frame with primary, secondary and tertiary datums so as part is immovable by translation and rotation. There are total 6 degree of movements, 3 in translation and 3 in rotation. In this feature control frame, the primary datum D, which is the bottom plane of a part. The part is located with the primary datum plane. The primary datum plane D restricts 3 degrees of freedom, one translation along the z axis and two rotations about the x and y axis. The remaining 3 degrees of freedom are unconstrained. This allows translation and rotation in other directions as shown. The part is free to move linearly along the x and y axis and rotate about the z axis in the xy plane. In this feature control frame, secondary datum is E, which is a back plane and controls 2 degrees of freedom. The secondary datum E prevents movement in two directions. No translation along the x-axis and no rotation about the z-axis. Datum F is the tertiary datum plane of left side of the part, controls 1 degree of freedom. Datum F restricts the moment of translation along the y-axis. Thus, the 6 degree of freedom is the datum reference frame define how a part can move or rotate. By using primary, secondary and tertiary datums, constraints are applied to prevent these movements, fully fixing the part in a space. 6 degrees of freedom is useful in understanding composite tolerancing. To illustrate this, let us consider a real-life scenario. Imagine we need to install an electric switchboard onto a wall that has ceramic tiles up to some specific height. The task is to mount the switchboard above these tiles. The electric switchboard is a ready-made product with a 100 mm distance between the mounting holes. Our job is to drill two holes in the wall to install the board. the first step would be to decide the correct position on the wall so that the switchboard can be mounted on that spot. Once the approximate location is determined, the next step is to create a drawing for the mounting holes on the wall. To do this, we define the coordinate axes x, y, and z to establish a reference origin point and direction for the dimensions. The sketch illustrates the two holes relative to the x, y, and z axis. Here is a drawing indicates two holes to be drilled in the wall with a 100 mm distance between their centers. Starting from the lower right corner, basic dimensions 50 are specified in both the x and y directions. Please note that sketches are not to scale and only purpose of explanation. Since there is no precision requirement like in machining parts assembly, a larger position tolerance can be selected for the mounting holes as we drill on the wall. Let us apply a 10 mm diametrical position tolerance to the mounting holes in the wall with reference to X, Y, and Z axis. The feature control frame would read as position of the two holes within 10 mm diametrical tolerance zone with respect to primary datum A, secondary datum B, and the tertiary datum C. Datum A is the wall surface, datum B is the lower side, and datum C is the right side as indicated by the datum symbols. The two mounting holes can be shifted horizontally within the given tolerance zone of 10 mm, and so as the electric switch box can also be shifted accordingly. Similarly, the holes can move up and down within the limits of the specified position tolerance zones. It is possible for the two holes to move independently in opposite direction, but within the given tolerance zone. In this case, the 100 mm center distance of the mounting holes on the switch box and on the wall would not match because on the wall the center distance is now increased. This is happened because of the larger tolerance zone given for the mounting holes on the wall. What would be the best solution in this case? One option could be to reduce the tolerance zone of the mounting holes. However, maintaining such tight tolerances from the wall corner's origin would be unnecessary and very complex. Now, let us try to analyze the situation. We have applied larger tolerance zone to wall mounting holes because there is no need to mount the switch box at a very precise position or the location. But on the other hand, the center distance of the mounting holes on the switch box is not as large or flexible as on the wall holes we apply. If we apply smaller tolerances, it is very stringent and unnecessary for the location of the switch box application. And if applied larger tolerances, center distance mismatch would be the problem. Composite positional tolerancing is the solution which addresses both the issues. Let us understand how it will be. Suppose 2 mm smaller tolerance zone is applied at the lower segment of the composite position tolerance zone. This smaller tolerance zone controls the relationship between the two holes, maintaining a required center distance. The upper segment has got larger tolerance zone and allows these two holes to move together as a pattern. It means the box location is more flexible, but center distance of the hole is not. How it is possible? let us see with the graphic. In this composite positional tolerance zone frame, at the lower segment, which is called as a feature related tolerance zone frame, a primary datum is repeated. As explained in the 6 degrees of freedom concept previously, the primary datum A prevents the rotation of the whole axis as shown in this animation. In the lower segment, datum A is repeated, which prevents the rotation but allows the holes to translate along the x and y axes as a group. It also permits rotation around the z axis in the xy plane. It also allows to rotate the features as a group within the pattern. This is how the whole pattern becomes floating in the linear x and y direction and also can rotate around or about the z axis. Now let us see the actual effect of this composite positional tolerancing on the switch box mounting on the wall. Because of the feature related tolerance zone frame, that is the lower segment, the center distance between the mounting holes are maintained. Thus, it solves the hole matching problem. But this group of holes are allowed to translate and rotate within the pattern tolerance zone. Because of this, switch box can be shifted to left, right, up, down, and also allowed to be tilted within the location tolerance zone. Linear shift is okay, but mounting of the switch box in tilted or oriented position on the wall, it doesn't look good aesthetically. This problem is still exists. To solve this tilting or rotation problem, we have to add one more datum in the feature related tolerance zone, that is in the lower segment. This would restrict the orientation or rotation of the features as a group in the pattern. Here it is repeated datum B, which is a bottom reference plane into the lower segment of feature related tolerance zone frame. Now let us demonstrate the effect of repeated datums in the lower segment. Datum A restricts the rotation of the axis. To simplify it, it controls perpendicularity of whole axis with respect to the datum plane A. Datum B, the lower side plane, stops the rotation of the group or pattern of whole features and allows only translation or linear movement of the whole pattern. Thus, with the application of the composite tolerancing, rotation of the switch box is restricted and only linear movements allowed within the pattern locating tolerance zone, that is within the upper tolerance zone. Summarizing the composite positional tolerancing. Composite positional tolerancing is a multi-segment tolerance zone frame. The upper segment is called as pattern locating tolerance zone frame with a larger tolerance zone control from the primary, secondary and tertiary datums. In this given case, the lower segment is a feature relating tolerance zone frame with a smaller tolerance zone. This tolerance zone control feature to feature relationship of the features, constraining translation and rotation of the features within the pattern. In the lower segment, one or two datums can be repeated. Primary datum repeated in the lower frame restricts the rotation of the whole axis, control particularity with respect to datum plane A. Secondary datum repeated constrain the rotation of the features or the holes in this case with respect to datum plane B within the pattern. Here is an engineering application where composite tolerances are applied. Linear motion guideways, commonly known as LM guideways. These guideways are the rails mounted on the machine bed and the machine structure with X, Y, and Z axis moving on these rails. Since both measuring and cutting machines require extremely high accuracy in the straightness parameter, the installation of the LM guideways becomes a highly complex process. Let us see by applying composite positional tolerancing how this complex installation becomes easy. The installation drawing for the LM guideways, where all the mounting holes follow a linear pattern controlled by the composite position tolerancing. The pattern is located within 0.1 from one of the corners of the two edges. To ensure straightness, the position of the holes must be highly precise. That is the reason why a tighter position tolerance is applied between the holes within the pattern. In the lower segment of the position tolerance, datums A and B are both repeated. This means the holes have some flexibility or more tolerance to move along the guide as this movement does not significantly impact the straightness required. However, the movement is constrained to just 0.05 across the guide to ensure that the guide does not vary in that direction and the straightness requirement is maintained. Thus, by applying composite position tolerancing, the rotation of the linear pattern is restricted. It allows only linear movement with the larger tolerances, and in which direction the straightness is important, it restricts with the smaller tolerance zone. Concluding why and when to use composite positional tolerancing. Advantages: efficiency. Composite position tolerances reduces the need for multiple tolerance specifications by combining location and orientation tolerances in one unified system. Flexibility allows the different level of precision for different parts of the feature. Improved functionality. It is particularly useful when the feature needs to fit within a large assembly or when complex geometry is involved. When to use it? When multiple features that need to be precisely located in relation to one another. When part must fit within the tight assemblies where multiple features need to align with greater accuracies. And when both location and orientation of features are critical.
Hope that you have liked this video, with very easy and simple explanations. You can comment how do you see this initiative and suggest more on upcoming videos. Also, we are pleased to conduct training programs at your locations in factories. We offer AUCOM Germany, an international CMM certification course. Basic of GD&T. Advanced GD&T. Stack up tolerances. Surface finish. MSA and other quality tools. For further details, please contact us. And I'm sure you will encourage the initiative of training through YouTube, by subscribing a channel. Accurate, ASME, ISO. Thank you and have a good day.
On behalf of Maini Precision Products, I would like to thank Mr. Momini a lot Okay, today what we have received is a very high quality of information. And if you have observed, I was also there in the class. Though I know little bit, but still I wanted to know more and more about it. So I also got enlightened with this. You understand? So though I was participating like you all, but still in the process I have received a lot of information. This particular section, training and interactive session was fantastic. If you all agree with me, it is fantastic. Understood? So this should not be the end. We should not leave this person. We should have to bring him quite often and take lot of informations from him and take what all problems we have. We have to ultimately see that, with his help, it is getting solved in our company. Is it okay?
Yes, sir.
Okay? So you must be ready. We will make you as a team. This team, complete team, will come for the next session. In the next session also he will be there and he is going to teach us a lot. Okay? Thanks a lot, Mr. Mohammed. Very, very, very nice interactive session. I hope you will also give more topics on this particular. This one.